thank you very much, and many thanks to the organizers for the kind invitation and for this opportunity to speak. This is not the first conference in the CAT series which I'm attending. I remember I attended one in the early 2000s. I spoke about A infinity Morita equivalence, so it must really have been a long time ago. Then I became too busy with applying DG categories to cluster algebras, and so I missed a few, but it is great to be back now for this special edition. And it is great to see how the subject has been flourishing, certainly not least thanks to the work of Bertrand, his collaborators and his students. And so I would like to wish Bertrand happy birthday and all the best for the years to come. Okay, so I will speak about cluster algebras with coefficients and relative Calabi-Yau structures. This is a relatively specific title, but in preparing the talk I realized that it would probably be better to focus on the big picture and a few basic definitions. So I will probably not get to the end. Maybe I will get about to this place. So for the experts who are interested in the more specific results, I would advise them to download the handout using this QR code or this link, and to jump to page 29. Okay. Yes, so here you have the plan. Yes, so the plan, I will start with a bit of history. Then I will define cluster algebras first without coefficients. And then I will perhaps come to cluster algebras with coefficients, and finally to their additive categorification involving relative Calabi-Yau structures. Okay, so let's start with this bit of history. It is actually essentially the history of links to other subjects. Cluster algebras were invented by Fomin and Zelevinski around the year 2001. All the years I'm giving are years of the preprints. So the preprint appeared in 2001, the paper was published in 2002, and if you look at the paper, you will agree with me that it's an invention rather than a discovery. And well, let me show you pictures of the two inventors, Sergei Fomin and Andrei Zelevinski. Andrei Zelevinski sadly passed away in 2013, just a few months before his 60th birthday conference. But Sergei Fomin is alive and well and extremely active. So, well, why did they invent these structures? Well, the cluster algebras are certain commutative algebras with a rich additional structure. So in particular, being a cluster algebra is not a property of an algebra, but a lot of additional combinatorial structure. And one and the same algebra can have many, many different such cluster structures. So why did they invent these structures? Well, the motivation came from Lie theory, and more precisely from the theory of canonical basis. Let me see whether I can make this work. Yeah, the theory of canonical basis. Canonical bases are certain vector space bases of quantum groups. They have wonderful properties, but they're extremely hard to construct explicitly. And in fact, it is unknown how to construct them explicitly. And Fomin-Zelevinski's aim was to find a combinatorial approach to the construction of canonical bases. Okay, yes, so canonical bases were developed independently at the beginning of the 90s by Lustig on the one hand, and by Kashiwara on the other hand. It is actually a non-trivial theorem that the bases which they defined are the same. Okay, then let's come to the links to other subjects. So more or less simultaneously with the invention, there was also the first application to a periodicity conjecture by Alexei Zamolodchikov for certain discrete dynamical systems, the so-called Y systems. They proved this for the Y system associated with a single Dynkin diagram. Later it was generalized. I will come back to that. Then also more or less immediately there was a connection to Poisson geometry. In Poisson geometry, cluster structures yield certain very well-behaved coordinates, log canonical coordinates. And Gechtmann, Shapiro, Weinstein have been working on a long-term project of introducing cluster structures on Poisson varieties. Then also very quickly, cluster structures were used in Fock-Goncharov's higher Teichmüller theory. Fock-Goncharov also introduced a more geometric view of Fomin-Zalewinsky's combinatorics. They considered a pair of varieties instead of just a single algebra, and this pair, they considered it these varieties dual to each other, and much later it was actually justified that they are dual in a sense, closely related to mirror symmetry. Then in 2004, or shortly before 2004, people realized that the combinatorics of cluster algebra are very similar to the combinatorics of tilting theory in the theory of quiver representations and representations of finite dimensional algebras. And this led specialists to the construction of certain two Calabi-Yau categories, the so-called cluster categories, and then later also three Calabi-Yau categories. So these are DG categories with Calabi-Yau structures, and that's how I got into the subject, by the way. And the philosophy is that of categorification. Yes, you have this rich combinatorial structure with rather mysterious properties. You have sequences of recurrence relations, and then you pass to the higher level of categories where you find natural explanations for the rather mysterious combinatorial phenomena which occur here. Yeah, so you would try to view the combinatorics as the shadow of phenomena which occur at the categorical level and which are much easier to understand, at least for people like you and me, at the categorical level. Okay, then in 2008, as you perhaps know, Kontsevich-Seubelman put an important preprint on the archive on DT theory, and in this preprint they also gave a DT theoretical interpretation of cluster transformations, and this was then fully developed to a beautiful link by Nagao in a preprint in 2010, published in 2013. Sorry. Then a little later, a new link to a different type of representation theory appeared, so-called monoidal categorification using representations of quantum affine algebras. This was already mentioned by Misha Kapranov in his talk on Wednesday. So here the philosophy is the same. Yes, we try to interpret the combinatorial structures as shadows of phenomena occurring at a richer categorical level. And here, well, the basic philosophy is very easy. Yes, we try to realize the given cluster algebra as the Grothendieck ring of a monoidal category, and representations of quantum affine algebras yield such monoidal categories. So from this point of view, this idea is quite straightforward. The analogous decategorification idea is much more complicated on this side. Okay. So we have these two types of categorification. In the additive categorification, direct sums in our categories correspond to products, and in monoidal categorification, tensor products in the category correspond to products in the algebra. So we have these two very different ways of categorifying the multiplication in the algebra. Okay, well, cluster theory had a lot of conjectures. Many of them are now solved, and a great many of them are solved thanks to the work of Gross, Hacking-Kiel, and Kontsevich in 2014. So they used tools from mirror symmetry to solve some of the conjectures, in particular the positivity conjecture in the general case. And they also constructed something which they called canonical basis, and which from their point of view is really canonical, but is actually very different from the canonical basis from Lie theory, as was discovered later. Okay. Then, well, let me mention one result which is important, which is given here. Yeah, so via this connection, people succeeded in proving Fomin-Zelevinski's main hope, namely that cluster algebras do indeed yield new information on canonical basis. Yes, during about 15 years, this was unclear. It was unclear whether the main motivation was actually something which was achieved by the theory, and this was then proved more or less independently, on the one hand by Kang, Kashiwara, Kim Oh, and Hsien around 2015. Okay, so well, this picture is actually incomplete. In particular, there are several links to different types of physics. And well, one would expect that after 20 years, this type of discovery of new links to other subjects should stop. But quite unexpectedly, there is a very recent new link to symplectic topology, so given by these two preprints. So in the first one, Casals and Gao use ideas from cluster combinatorics to solve an old problem in symplectic topology, namely they construct infinitely many Lagrangian fillings for certain Legendrian torus knots. This was an open problem, so they import ideas from cluster theory, and then in the second preprint, in this 6-author preprint, they go the other way. They use symplectic topology to prove the existence of cluster structures on a large class of varieties, the so-called braid varieties, and this solves a lot of open problems in the subject. Okay. Well, now we may ask, how is this linked to the subject of this conference? Well, first of all, of course, these DG categories are objects of non-commutative derived geometry, as Massimo reminded us yesterday. And well, that was my motivation for beginning to study cluster algebras. Then, perhaps more surprisingly, derived modular stacks appear. They appear in this very recent work by the 6 authors. So the 6 authors prove their theorem by realizing braid varieties as certain derived modular stacks. Derived modular stacks which in the end turn out to be concentrated in degree 0 and to be very nice affine irreducible smooth varieties. But it is their realization as derived modular stacks which allows them to put all the extra combinatorial structure on these varieties. Okay, and then, well, one of the, I think, very interesting and open problems, yes, is to find a link between these two types of categorifications. Yes, additive categorification with sums corresponding to products and monoidal categorification with tensor products corresponding to products. And so one would hope for a close link because, well, these categorifications are very hard to construct, but when we have them, they are very powerful. Yes, in particular, they allow to prove Fomin-Zelevinski's main hope. On the other hand, additive categorifications are quite easy to construct. Essentially, what you need is a quiver with a non-degenerate potential. And, well, they are less powerful. They are also very useful. Yes, so for example, they served in proving a generalization of the periodicity conjecture. But, well, so how it would be great if we could construct monoidal categorifications starting from additive ones. And, well, it is my expectation that if this problem is solved one day, then I would expect that derived modular stacks should play an essential role. But, okay, this is, of course, complete speculation, and let me not try to speak more about it, but instead give you a few pictures of some of the main contributors. Yes, maybe you recognize some faces. Yes, here, Kontsevich, for example, or Masaki Kashiwara, or some of you may know Mark Gross. Then Bernhard Leclerc. Bernhard Leclerc appears twice, yes, here with his collaborators on additive categorification using representations of pre-projective algebras, and here for his work with David Hernandez on monoidal categorification. Okay, so now let me come to the second section. Cluster algebras, for the moment, without coefficients. Well, they are associated with a very basic combinatorial structure, namely the structure of a quiver. If English is not your mother tongue, you may not know what a quiver actually is. So here are pictures of quivers. Yes, a quiver is a container for arrows. Yes, I don't know whether you recognize this mathematician. He works on a subject very much related to quivers. It's Hiraku Nakajima, yes, the inventor of Nakajima quiver varieties, with a Japanese version of a quiver. Okay, now in mathematics, well, I suppose you know this definition, but let me just fix the notation. A quiver is given by a set of vertices, denoted usually by Q0, a set of arrows denoted by Q1, and then for each arrow we are given its source and its target, S and T of the arrow. Then, well, it's a category without composition and without identities. A quiver in general is non-connected. And let me give you a bit of terminology. So here we call alpha a loop. A loop is an arrow going from a vertex to itself. And then we have beta and gamma, which form a two-cycle. And we have vertex number 7, which is a source of the quiver, a vertex with only outgoing arrows. And dually, number 6 is a sink of the quiver, a vertex with only incoming arrows. Okay, and now let's fix a finite quiver without loops and without two cycles. For such quivers, one can define an elementary operation, the mutation, and this is the first basic combinatorial ingredient of the definition of cluster algebras. So let us fix a vertex of the quiver, and then we define the mutated quiver to be obtained from the quiver Q in 3 elementary steps. So first, for each path of length 2 passing through the mutating vertex, we adjoin a new arrow, a kind of formal composition of the two arrows alpha and beta. Then, in the second step, we reverse all arrows with source or target the mutating vertex. And finally, we remove the two cycles. Yes, in the first step, we may have created 2 cycles. In the last step, we remove all of them. And this is not quite canonical. Yes, if we have 3 arrows going back and forth between 2 vertices, we have to choose 2 among them, throw them away, and keep the third one. So it's not quite canonical, but it's unique up to isomorphism fixing the vertices, which is enough for our purposes. So let's look at a simple example. Let's take this 3 cycle and mutate it at the vertex number 1. So in the first step, we have to add the formal composition of these 2 arrows. In the second step, we have to reverse the 2 arrows incident with 1. And in the third step, we have to remove the 2 cycles. So that gives us this quiver. So notice that this is quite a drastic operation on the quiver, both from the point of view of topology. Yes, we pass from a circle to an interval, and also from the point of view of quiver representations. Yes, the representation theories of these quivers have nothing to do with each other. But, well, it is the basic ingredient, and it's useful and important to do bigger examples. And for this, well, you can download an applet here. Yes, this is, I have two ways of understanding combinatorics. The first one is programming. The second one is categorifying. So let's start with the programming. Okay, I think. Yeah, so if you download here, you can download this applet, which I'm going to use now. Yes. Okay, so this is a bit too big to start. Let's start with the one which we have just done by hand in the same series. Sorry. Okay. Yeah, in this applet we mutate by clicking on the vertices. So if we click on this vertex, then this arrow should disappear and these two should be reversed. Click, and this is actually what happens. And, well, if we do it again, click, we get back to the original quiver, and this is a general phenomenon which you can prove as an exercise if your mutation at a fixed vertex is an involution. Okay, well, let's look at one more mutation. If we mutate at the source with only outgoing arrows, well, then, as you can easily check, mutation will just reverse the outgoing arrows, like this, or more, or here we have another source. If we click, the arrows are reversed, and dually, if we have a sink, the incoming arrows are reversed. So this, okay, I think we have understood this first simple example. Let's look at a slightly bigger one. Okay, well, it's more complicated, glued together from 3 cycles, but I claim that in just 4 mutations, I can transform it into a quiver without any oriented cycles. So for this, let me first deform the picture slightly. Yes, this has no incidence on the quiver. The quiver is an abstract graph, but the pictures will look nicer. So what is going to happen if I mutate at this vertex, number 5? Well, quiver mutation is essentially a local operation, and so locally what's going to happen is the thing that happened in the first example. So these 3 arrows have to disappear, and then here you see we have this chain at the bottom, and this should lead to the creation of a new arrow at the bottom. Click, yes, this is what happens. Now we can easily get rid of this 3 cycle by mutating at 6, and we can easily get rid of the 4 cycle by mutating first at 3 and then at 1. Okay, and now you can see we get a nice graph, an orientation of the D6 Dynkin diagram. Yes. There's a graph layout algorithm built into the applet. Okay. Well, these first examples look very nice and innocent, and they are actually deceptively simple, because in reality, quiver mutation is a chaotic operation. Let me show you why. Let's start with this quiver. Yes, we can still try to simplify it using mutations, but it's not clear how to do that. So let's just do something random. Let's do, say, 15 random mutations. Okay, the quiver changes a bit. Let's do 15 more random mutations. Okay, more changes. Okay, let me repeat it once more, and again, and again, and again, and again, and again. And now something has happened. Yes, you see this 2, for example, on this arrow. The 2 means that we actually have 2 arrows. It's the multiplicity of the arrow. Okay, so we get arrows with multiplicity. Let's do 15 more random mutations. Okay, more changes. And now higher multiplicities, and higher, and we get this type of explosion. Yes, and this is the typical behavior. Yes, this is an example of a wild quiver. Almost all quivers are wild, and if you mutate a wild quiver in a random way, then you get this type of explosion. So you get these enormous numbers, and yeah, which appear and which are, well, part of life. Yes. So since they appear here, and this is linked to canonical basis, they will also appear in canonical basis. So that shows you that canonical bases are very complicated as well. Okay. Yes. Then let me continue here. Okay, this quiver is actually very nice as far as mutation is concerned. Its mutation class is finite. It's the last in the series with finite mutation class. The mutation class contains about 5,800 quivers. Here you can see 2 of them. Each of them contains at least 1 cycle, which you can check by brute force or by categorification. And now, remember, we want to define cluster variables and cluster algebras. And for this, we need to enrich this purely combinatorial datum of the quiver a little bit. We have to pass from quivers to so-called seeds. What is a seed? It's a pair consisting of a quiver with n vertices labeled from 1 to n. And then, in addition, we are given n fractions in indeterminates x1 up to xn, and these fractions should form a free generating set for this field of functions. Okay, so if you can also think of this datum, of course, as an automorphism of the field, given by the images of the xi's, which are the ui's, but I will stick to this very basic viewpoint where we just consider this as an n-tuple of fractions. And now we can extend the mutation operation from quivers to seeds. But before, let me introduce a bit of notation. So here we have an example of a seed called the initial seed associated with this quiver, where for the ui's I just take the indeterminates themselves. And I will abbreviate this by writing the indeterminates instead of the vertices. And then we can extend the mutation operation. We mutate the seed. So at the level of the quiver, this is just the mutation operation which we have just seen. And at the level of the seed, well, we take the expression uj associated with the mutating vertex, and we replace it with a new one. And we leave all the others alone. And the relation between the old and the new expression associated to the vertex I is given by this exchange relation. So new times old is the sum of 2 monomials, a monomial over the incoming arrows plus the monomial over the outgoing arrows of the expressions associated with the sources, respectively the targets of the respective arrows. Yes, so this is one of the central ingredients of the definition. Yes, so you have a product of 2 things, which is the sum of 2 monomials. So when you're in a situation where you see a product of 2 things, which is the sum of 2 monomials, then it might be that you're in presence of a cluster structure. A typical example being the Grossmanian with the Plücker relations, which are exactly of this form, and which Misha Kapranov already mentioned. Okay, so this is the way we mutate seeds. So let's look at an example. Well, we take this A3 type quiver. This is the initial seed corresponding to it, and say we mutate at the first vertex. Then, well, we have no incoming arrows. This is a source, so the quiver in quiver mutation just reverses this arrow, okay. Then x2 and x3 remain the same. And x1, well, to compute x1, we have to take the product over the incoming arrows. There are none, so it's an empty product, plus the product over the outgoing arrows. There's only this one with target x2. And then at the end, we have to divide by x1. So this gives us this expression, product over the incoming plus product over the outgoing arrows divided by x1. And then, well, of course, if we do mutation at x2, well, the quiver, which is a chain, becomes a cycle. x1 and x3 remain unchanged, and here we take product over incoming plus product over outgoing divided by x2, and that's our new seed. Okay, and then of course we can iterate this procedure, and well, if we do mutation at 1 again, we will get back to the initial seed. So mutation of seeds at a given vertex is an involution as well. But we can mutate at 2 or 3, etc., and we get potentially new seeds in our class, new seeds. So we get this large tree with triples of rational expressions associated to each vertex. So these triples of rational expressions are called the clusters of the cluster algebra associated with this quiver, and the expressions themselves are called the cluster variables, and the cluster algebra is the subalgebra of the function field generated by the cluster variables. So here I have the official definition. We start from a quiver, then we have the initial seed, we start mutating the initial seed, then we get these n-tuples appearing in the mutations. Those are the clusters. The elements of the clusters are called cluster variables, and the cluster algebra is the subalgebra generated by the cluster variables. Then one more piece of terminology, a cluster monomial. It's a product of powers of cluster variables all belonging to the same cluster. And well, this is important in view of canonical basis, because the main hope, which is now confirmed, is that in the examples where the canonical basis is defined, it contains the cluster monomials. So these expressions should all be part of the basis. And well, the cluster algebra is an invariant of the mutation class of the quiver, which is essentially clear from the construction. And now let me do a computation. Yes. Okay, let's look at two simple examples just to see what is going on. So we add a second node and we add an arrow from the first to the second node, and we're done. And now, well, we form the initial seed. Here we have the initial seed, x1 and x2, associated to the two vertices. And we start mutating. Well, let's mutate at 1. Okay, the arrow is reversed, and we have one new cluster variable. We replace the x1 here with this new expression. If we mutate again at 1, we get nothing new, so we mutate at 2. Okay, we get this expression. And if we now mutate again at 1, we get this expression, and we go back, and we find a periodicity of length 5. And we also observe some other remarkable phenomena, namely these expressions are all Laurent polynomials, which is not clear at all. Yes, at some point you have to divide by, for example, to compute this, you have to divide by this expression, which is not a monomial, and so it is quite remarkable that here you still get a Laurent monomial. And then you also see that the coefficients in the numerators are all positive. Well, here in this very simple example, they're all 0 or 1. But let's look at a slightly bigger example. Yeah, please.
Cluster variables are all of these?
Yeah, all of these expressions, all the expressions which you get by iterated mutations are cluster variables.
Actually, you take also the original ones, so it's fine.
Yes, they are part of the cluster variables, yes.
Can I also ask, so in your definition of the seeds,
Yes.
the U's generate
Yeah, you can check that they will again form a free generating set, yes.
Yes, that then confuses me, as what are they generating?
As a field, free generating set of the field of rational functions.
And then
And the cluster algebra is the subalgebra generated by the cluster variables, yes. This is an important point, yes. Yeah. More questions? Yes?
Just to be sure, the fact that this loops is not a general fact.
This is not a general fact, it's a very special fact, and we will see the general statement which is behind it. Okay. Okay, let's look at the second example. Okay. We add a node, and now we take two arrows from 1 to 2, or one arrow with multiplicity 2. Yeah, sorry, the 2 is a bit small, but it is there. Yeah, this is the so-called Kronecker quiver, two arrows linked by two vertices linked by two arrows. Okay, let's again compute some cluster variables. Okay, well, we start with the initial ones. Okay, and we start mutating. 1, 2. The quiver doesn't change, yes, only the orientation of the quiver changes. But as you can see, the expressions become more complicated. Yes, but they remain Laurent monomials, yes? All the denominators are monomials. Okay, and well, I will not do the computation too far because otherwise the computer will freeze and I would have to stop immediately. So, well, anyway, you see that we still get Laurent monomials and we still get positive coefficients in the numerators. Okay, and this is a general phenomenon. But now, well, as you can see more or less immediately, we get infinitely many cluster variables, yes? So we get infinitely many generators for this algebra. In fact, the algebra is finitely generated in this case, but the cluster theory gives us an infinite set of generators. Okay. Yes, so let me...
Does it turn out to be a linear basis for the algebra?
Pardon?
Does it turn out to be a linear basis for the algebra over the ground field?
So in this example, in the first example, the cluster monomials form a basis of the Q vector space underlying the algebra. And well, for a connected quiver, this happens if and only if the underlying graph of the quiver is an ADE-Dynkin diagram. And in the second example, it is not a Dynkin diagram, and the cluster monomials don't form a basis, but there's only one family of monomials missing, associated with the tube. Yes. Okay, so let me state the theorem. First of all cluster variables are Laurent polynomials in complete generality. And, well, we had these two examples. The first one with finitely many, namely 5 cluster variables. The second one with infinitely many. So here is the theorem for connected quiver. If there are finitely many cluster variables, if and only if the quiver is mutation equivalent to an orientation of an ADE-Dynkin diagram. So for the triangle which we had at the beginning, yes, that was mutation equivalent to D6, and so in that example we have finitely many cluster variables as well. Okay. And yeah, we have already seen examples. And now we have we also observed positivity of the coefficients, and this is now a theorem. It was conjectured by Fomin-Zelevinski in their original paper, and it also took a long time to prove. It was first proved for quivers by combinatorics, extremely ingenious combinatorics, by Ralph Schiffler and Kyung-Yong Lee in 2013. But actually, Fomin-Zelevinski's conjecture was in a slightly more general setting, namely in the setting of valued quivers. Yes, valued quivers, for example, corresponding to the BCFG Dynkin diagrams, the non-simply laced Dynkin diagrams. And this additional generality is important in view of Langland's duality, of course. And so this more general conjecture was proved, well, that was beyond the combinatorial means, and it was proved by Grosecki, Kiel, and Kontsevich using scattering diagrams and broken lines, yes, imported from mirror symmetry in the Strominger-Yau-Zaslow approach. Okay. Okay, now we come to, yes, I don't know how much time do I have left? 20 minutes. Oh, great. Then I need to slightly change the, okay, the method. Yes. Okay, so now we come to cluster algebras with coefficients. So why do we need coefficients? They are essential for at least two purposes. So the first purpose is that, well, we want to identify our cluster algebras with something geometric, as with coordinate algebras of varieties. And whenever we do that with a reasonable variety, we will need coefficients. If we can, of course, look at the spectrum of a cluster algebra without coefficients, but it will be very degenerate. And then the second purpose is when we want to glue cluster algebras, which essentially means gluing quivers, then we need the coefficients, which will correspond to certain distinguished vertices in the quiver. For example, this is important in Fock-Goncharov's theory. And so for this, we need a slight extension of the notion of quiver. We need an ice quiver. That's a pair consisting of a quiver and a subquiver F, F like frozen. So this subquiver F is called the frozen part. And now here we have examples, each with the corresponding variety. So here in the first example, I will explain how to get the cluster algebra in a minute, but in this case, the associated cluster algebra will be canonically isomorphic to the coordinate algebra of this group of unitriangular matrices. Yes, well, of course, this group as a variety is just affine space, but it has a non-trivial cluster structure, and this cluster structure is related to the fact that it is the maximal unipotent subgroup in SLN. Okay, then here we have a second example. This example yields as a cluster algebra the homogeneous coordinate algebra of the Grassmannian of 4-dimensional planes in 9-dimensional space. Well, more precisely, you see this little hat. More precisely, it's the Plücker cone over this Grassmannian. And then here we have an example from Fock-Goncharov's theory. This is the associated cluster algebra is the algebra of coordinates on a certain moduli space of PSL3 bundles on the disk with 3 marked points on the boundary. And here you can see that the frozen subquiver in this example is not a full subquiver. Yes, here we have 2 frozen vertices with a non-frozen arrow between them.
Sorry.
Right.
The coordinate algebra cluster algebra is?
The cluster algebra is some commutative algebra, and we want to realize it as the coordinate algebra of a variety. Or actually, conversely, we are given the coordinate algebra of a variety, and we want to write it as the cluster algebra, as a complexified cluster algebra, to be precise. Okay. Okay. Okay, so how do we get the cluster algebra when we are given the ice quiver? Well, we do essentially the same, but we never mutate at the frozen vertices. So we have our vertices, the non-frozen ones and the frozen ones, numbered like this for convenience. And, well, we take our initial seed and we mutate it, but we only mutate it at non-frozen vertices. And then there's a refinement of the Laurent phenomenon, namely the cluster variables which we get in this way by iterated mutation. They are Laurent polynomials in the initial cluster variables x1 up to xn, but they are true polynomials in xn plus 1 plus xm, and these are called the coefficients. And now we can define at least 2 natural algebras associated with this setup, namely, well, first the one with non-invertible coefficients, where we take the subalgebra over the polynomial ring generated by the cluster variables, or we can localize it with respect to the coefficients. That gives us the cluster algebra with invertible coefficients, which is, both are useful and important. And, well, here you have the precise recipe, how to establish the isomorphism between the complexified cluster algebra of this ice quiver and the coordinate algebra of the upper unitriangular 3×3 matrices. And, well, when we localize, we get a certain open subset. Here we have the same for the Grassmannian. Yeah, it's a particularly nice example. It was proved in Scott's thesis under the supervision of Zelewinsky that this coordinate algebra, homogeneous coordinate algebra of the Grassmannian, is a cluster algebra, and the cluster structure is given, for example, by this quiver, together, of course, with an assignment of the initial cluster variables to certain functions here.
Excuse me, what is the impact of an arrow to be frozen or not?
Excellent question. Actually, the frozen arrows have no influence whatsoever on the cluster algebra. So they will change in mutation, actually by a slightly different rule than the one I gave, but they have no incidence on the cluster algebra, and that is why Fomin and Zelewinsky and many people after them just don't draw them. They just neglect them, but well, if you want to glue, then you do need them, yes. You do need them as soon as you want to glue cluster algebras or the corresponding categories. Yes. So if you look at a single cluster algebra, they play no role whatsoever. And in fact, if you only look at the combinatorics of the cluster algebra, then the whole frozen part doesn't matter. But, well, if you look at the variables, then they do matter. Yeah. Okay. Yeah, more questions? Yes. Yeah. So in Fomin-Zelewinsky's theory, arrows between frozens are neglected, but not in Fock-Koncharov's theory. If you look at their papers, they represent them by half integers in antisymmetric square matrices. Yes. And Fock and Koncharov need them because they want to glue. Yes, they want to glue their Teichmüller moduli space by gluing triangles. Okay, yeah, so let's get back to this example of the Grassmannian. Yes, so the initial cluster variables correspond to certain Plicker coordinates, and then we get an isomorphism, and in this isomorphism, all the Plicker coordinates turn out to be cluster variables, and there are no others if we look at a Grassmannian of planes, but as soon as we look at Grassmannians of higher dimensional subspaces, we have many more cluster variables than Plicker coordinates. Then we have the Plicker relations, which are very nice examples of exchange relations. And again, well, we can either invert or not invert our coefficients. And, well, if we invert them, then we get the coordinate algebra of what the combinatorialists call the big positroid cells. Okay, and now I have 5 minutes left, yes? Even more. Okay, then we can quickly categorify. Pardon? 12 minutes. 12 minutes? Oh, great. Okay. Okay, so, well, then let me remind you of relative Calabi-Yau structures. First, what is the philosophy? Well, a Calabi-Yau structure on a DG category is analogous to an orientation on a manifold, and from this viewpoint, a relative Calabi-Yau structure on a DG functor, yes, you can also omit the word relative if you, but I will use it. A relative Calabi-Yau structure on such a DG functor is analogous in the same spirit to an orientation of a manifold with boundary. Yes, the boundary B B like boundary corresponds to this DG category, and we are given an orientation on this manifold with boundary, which corresponds to a relative Calabi-Yau structure on the DG functor. So this notion is due to Bertrand, who first discussed it in his survey for the European Mathematical Society in 2014. So it's a 90-page survey, and on page number 288 you can find this notion. Actually, the notion itself only occupies 1/3 of a page, and 2/3 of the page are occupied by a very interesting example related to whole multiplication, which you promise to continue in a different article. You don't even write future article, but different article. I don't know whether... Yeah.
Let's talk after.
Yeah, let's talk afterwards.
Remind me what I have to do.
Yes. Yes, I think it's actually very interesting, in particular in view of this class of examples. Yes. Okay. Yes, so they were invented by Bertrand, but then they were developed in two beautiful papers by Chris Bruff and Tobias Deckerhoff. So they introduced two versions of this notion, which are essentially causal dual to each other, left and right. So this was for the left version. And why are they important? Yes, again, well, when you have a manifold with boundary or several manifolds with boundary, you can glue them. Yeah, so that's the interest of having a boundary. And that was one of Bruff-Deckerhoff's main results, that they allow you to glue Calabi-Yau categories. Okay, and well, this idea of gluing, yeah, it is natural to try and apply it in cluster theory, and this has already been done by Merlin, who is present among us. So he has constructed categorifications of surface cluster algebra. So this is classical Teichmüller theory using relative Calabi-Yau structures, and I'm sure he will be glad to discuss this over lunch. Then a very quick remark. Well, we have a rich source of relative Calabi-Yau structures, namely the so-called relative D-Calabi-Yau completions introduced by Young in 2016. And thanks to the work of Bozek, Kalak, Shirotsky, we know that this is just the non-commutative equivalent of a 2 minus D shifted conormal bundle. And well, to avoid any misunderstandings here, I have given you the construction of the relative D-Calabi-Yau completion. We take two smooth DG categories, and then we associate such a DG functor with it. Maybe I will skip the details. And now, well, now we are given an ice quiver. So our quiver is, as usual, finite without loops or two cycles. Then we have the completed path algebra. I will just write KQ, but it's always completed. We choose a potential which should be in generic position, which means that it should avoid a certain countable union of hypersurfaces. Pardon?
Do you modify path algebra in accordance with ice structure or no?
With which?
Do you modify the path algebra?
Yes, this is just the ordinary path algebra, so this doesn't take into account frozen or unfrozen errors. It's the path algebra of the whole big quiver. Yes, frozen part included, right? And then we have KQ, we have a potential on the whole quiver again, and then we have associated with it, well, what one can call the associated Ginzburg morphism. Yes, these algebras are often called Ginzburg algebras, in particular the one of dimension 3. So, okay, so this is a construction which starts from the ice quiver and the potential and produces as an output DG algebra morphism between two DG algebras, B and A, B for boundary as always. So here B is the 2 Calabi-Yau completion, or the non-commutative cotangent bundle of this one-dimensional object. Yes, the path algebra is of global dimension 1. And it sends an arrow to this three-dimensional relative Ginzburg algebra associated with the quiver and the potential. And well, here you have the precise construction, very explicit. Yes, so here you have this two-dimensional Calabi-Yau completion. You add an arrow in the opposite direction, still of degree 0. You add loops of degree -1, and the differentials of the loops give you commutators between old and new arrows. Then here, this is a variant of the Ginzburg algebra, which we have seen in Jünsch's talk. Yes, the relative variant, where we adjoin opposite arrows for the non-frozen arrows only. We leave the frozen arrows alone, and we adjoin loops for the non-frozen vertices only. Then the differential is the one you would expect for the new non-frozen arrows in degree 1, and for the loop, sorry, I forgot the differential of the loop, but it's again the commutator between old and new arrows. And well, as you can see here in this rule, we use the cyclic derivatives of the potential only with respect to non-frozen arrows. But when we look at the definition of this morphism, then we also use the cyclic differential with respect to the frozen arrows. So the whole information of the potential is actually included in the definition in the construction of this Ginzburg morphism. Okay, and this, I hope I said it somewhere, this carries a canonical relative three Calabi-Yau structure as shown by Young. Okay, so let me abbreviate the boundary algebra by pi and the DG Ginzburg algebra by gamma. Then I construct a category which will allow us to lift the cluster combinatorics. So, well, we have gamma, we have its unbounded derived category. Inside we have the perfect category, which is also the thick subcategory generated by the free module of rank 1. And then for each vertex we have a simple one-dimensional gamma module. Okay. Yeah, so in the absolute case, these would give us 3 spherical objects in the derived category. Here, the ones associated with frozen vertices don't give us 3 spherical objects. Then a bit more notation, add of gamma for the closure under coproducts and retracts, and then this EF for the frozen idempotent, and then we define two categories, the so-called relative cluster category, which is the Verdier quotient or DG quotient of the perfect derived category of gamma by the thick subcategory generated by the non-frozen simples. And so this is a triangulated category or a pre-triangulated DG category, and as a full subcategory it contains what we call the Higgs category, which is not stable under shifts. So it just consists of these cones over objects in the additive closure of gamma, and the morphism of the cone should satisfy this extension property with respect to the frozen objects. Yes, the frozen DG modules obtained from gamma. And now we need to make, in order for this construction to have nice properties, let's make 2 finiteness assumptions. Maybe I will not enter into the details of these finiteness assumptions, but under these assumptions, the Higgs category is closed under extensions, and it has a 2 Calabi-Yau property. X1 is symmetric in the sense of cell duality. Okay, let's look at what we get if we apply this construction in the case of the Grassmannian. Okay, well, so this is our quiver, and we endow it with a canonical potential. Yes, there is one most canonical potential which you can associate with this. You take the sum of the positively oriented triangles minus the sum of the negatively oriented triangles, and then plus or minus the sum of these 2 cycles. Okay, and then, well, so if you look at the frozen part, yes, you recognize a cycle, and in this case, the two-dimensional Ginzburg algebra is just isomorphic to the classical preprojective algebra. It's concentrated in degree 0, and actually this relative Ginzburg algebra is also concentrated in degree 0. It gives us this certain algebra A. We have the Ginzburg morphism, which now induces a usual algebra morphism from B to A. We can look at its image, which gives us a certain subalgebra C. So B and A are smooth, yes, by construction, but this image subalgebra is singular. And, well, it's singular, but not too badly singular. It is still a Gorenstein. Namely, and so we can look at its category of Cohen-Macaulay models, as it turns out to be Noetherian as well. We look at finitely generated Cohen-Macaulay models, so modules which, for which the algebra itself behaves like an injective module. And this gives us a concrete description of the Higgs category in this example. So in particular, you see it's not abelian, it's not the heart of a T structure. And the generalized cluster, the relative cluster category in this case identifies with the derived category of this exact category of Cohen-Macaulay modules. And then, so this was the example, and now in the general case we can continue. We need a decategorification map. So this decategorification map, well, here I have defined it for the Higgs category. Well, I have not defined it, but I state its existence. So you can write it down explicitly and in geometric terms, in terms of Euler characteristics of Grassmannians of sub-representations. And so we get this map, and it categorifies in a strong sense. Yes, one can lift all the combinatorics. Here I have just stated this basic theorem which gives us a categorical lift of the cluster variables. And so to end, I think I need to end, yes. Let me say what a cluster character is. So this is the decategorification map in the additive case. Yes, in the monoidal case, it is very simple. It just takes an object and sends it to its class in the Grothendieck ring. In the additive case, it is given by such a cluster character, so which only depends on the isomorphism class. It transforms sums into products, and then the most important relation is this one, which generalizes the exchange relation. Yes, in the exchange relation, the product of two things is the sum of two monomials, and this is encoded in the triangulated structure when we have two objects with one-dimensional X space, and by the two Calabi-Yau property, this is one-dimensional in both directions. So we have two non-split triangles whose middle terms are well determined up to isomorphism, and what we get is, well, we take the product of these two, and that's the sum of the images of these two middle terms of the triangulated sequences. Yes, so the moral is that the combinatorics are included in the category together with its triangulated structure and together with its Calabi-Yau structure. And I'd like to stop here. Thank you very much.